Somewhere in the rainforests of Southeast Asia, there is an insect that can turn itself into a bomb. Not metaphorically, not as a figure of speech. When threatened, it tightens the muscles in its own body until its skin ruptures, spraying a toxic yellow liquid across everything nearby, including itself. It does this on purpose, and it dies the moment it does. For decades, biologists assumed this had to be some kind of malfunction, a stress response gone wrong, an accident of evolution that happened to look dramatic. But the more they studied it, the more they realized something unsettling. This isn't a glitch, it's a weapon, one so effective that it has evolved independently, in different forms, in different corners of the animal kingdom. And understanding why it exists means rethinking what we assume a living creature is even willing to do to protect the group it belongs to. Let's start with the ant itself. Its name is Calabopsis saundersi, though for years it was known by an older name, Camponotus saundersi, and either way, most people just call it the exploding ant. It lives high in the rainforest canopies of Malaysia, Borneo, and Thailand, building nests in trees far above the forest floor. From the outside, it looks unremarkable, a dark, narrow-bodied ant, slightly larger than average, moving in the same disciplined columns you'd expect from any social insect. But look closer, and you'll notice something strange about its abdomen. It's oversized, swollen almost compared to related species, and inside that swollen abdomen is where the mystery begins. Running the length of its body are two enormous glands, packed with a thick, sticky, yellow secretion. In most ants, glands like these are modest, tucked away, used sparingly. In this species, they take up so much internal space that they press against nearly every other organ the ant has. It is, in a very literal sense, built around its own payload. So what is that payload for? For years, entomologists debated it. Some assumed it was simply a stronger version of the chemical sprays other ants use to repel predators. Nothing more than pepper spray with better branding. That explanation held up right until researchers actually watched what happens when the ant deploys it. When a Calabopsis saundersi worker is cornered, usually by an invading ant from a rival colony, it doesn't run. It doesn't retreat toward the nest to call for reinforcements the way most social insects do. Instead, it grips its enemy and begins to contract its abdominal muscles with tremendous force. The contraction isn't gradual, it's sudden and violent, and within moments, the exoskeleton around its abdomen simply gives way. It ruptures, not metaphorically ruptures, splits open. And when it does, that yellow secretion doesn't just leak out. It's under enough internal pressure that it sprays, coating the attacker, coating the surrounding area, sometimes coating several nearby combatants at once. The chemical is intensely sticky and, in many cases, toxic or irritating enough to immobilize or kill the ant on the receiving end. The exploding ant does not survive this. There's no scenario where it does. It has essentially converted its own body into a single-use chemical weapon, and the explosion is the trigger. That alone would be strange enough. But here's where it gets stranger. This isn't a random defense mechanism. It's not something the ant does out of panic, indiscriminately, the way a frightened animal might lash out. This behavior is reserved almost exclusively for one specific threat: swarms of much larger, far more numerous ants, most notably marauder ants, a genus known for overwhelming rival colonies through sheer numbers. A single Calabopsis saundersi worker has no chance against a marauder ant in a straight fight. It's smaller, weaker, and outnumbered. In evolutionary terms, that worker's odds of winning are close to zero no matter what it does. So evolution appears to have optimized for something else entirely. Not winning the fight, winning the war. Because here's the detail that changes everything. That sticky yellow explosion doesn't just kill or disable the ant it targets. It coats the surrounding area in a substance that other invading ants have to physically extract themselves from. It clogs their mandibles. It slows their advance. A single exploding ant dying in the process can disrupt or damage several attackers at once and buy critical seconds for the rest of the colony to respond, seal tunnels, or evacuate vulnerable areas of the nest. In other words, this individual ant isn't fighting to survive. It's spending its own life as currency, purchasing time and protection for thousands of genetically related ants back in the nest. And that reframes the entire question. Because in evolutionary biology, an individual sacrificing itself for the group only makes sense under very specific conditions. This is where the story stops being about ants and starts being about something far bigger: the strange mathematics of self-sacrifice in nature. For most of the 20th century, evolutionary theory struggled to explain any behavior where an individual reduces its own chance of survival to help others. If evolution rewards traits that help an individual pass on its genes. Why would natural selection ever favor a trait that guarantees death? The answer came from a concept called kin selection, developed in the 1960s, largely through the work of biologist William Hamilton. His insight was simple but radical. Genes don't need the individual carrying them to survive in order to be passed on. They just need copies of themselves to survive, somewhere in someone. And in a colony of ants, nearly every worker is a close genetic relative of the queen, and by extension of every other worker. So from the gene's perspective, an individual worker dying to protect the colony isn't really a loss. If that sacrifice saves the queen, and the queen is the one actually producing the next generation, then the genes responsible for the self-destructive behavior get passed on anyway, just through her offspring instead of the sacrificed worker's own. This is why the phenomenon shows up almost exclusively in what biologists call eusocial species. Ants, termites, some bees and wasps, all species built around a single reproducing queen and an army of closely related, mostly non-reproducing workers. In those colonies, the individual essentially stops being the important unit of survival. The colony is. And once you see it through that lens, the exploding ant stops looking like an anomaly and starts looking like the logical endpoint of a very old evolutionary trend. Because it isn't alone. In the rainforests of French Guiana, there's a termite, Neocapriderms terracua, that does something even stranger. As these termites age, they develop small blue crystals inside pouches on their abdomens, made of a copper-based compound. When a young termite fights an intruder, it fights normally. But when an old termite, one nearing the natural end of its working life, is cornered, it rams itself into the enemy and ruptures those crystal-filled sacs. The blue compound instantly reacts with a separate chemical stored in its jaw, creating a toxic reaction that damages or kills the attacker and the termite itself. What's remarkable here isn't just the mechanism, it's the timing. Younger termites, the ones with the most potential years of labor left, do not explode. Only the older ones do, the ones closest to the end of their useful life anyway. Evolution appears to have tuned the termite colony's self-destruct sequence to activate at the exact point where an individual has the least future value left to lose, and the sacrifice becomes, in a cold evolutionary sense, nearly free. It's the insect equivalent of retiring into the front line. Aphids do something structurally similar. Certain species produce specialized soldier aphids, sterile individuals whose entire biological role from birth is defense. When a predator attacks the colony, these soldiers can rupture their own bodies, releasing a sticky substance that entraps the threat, sacrificing themselves in a single, final act that they were, in a sense, built for from the moment they hatched. None of these species evolved this trait by copying each other. Termites, aphids, and ants split off from separate evolutionary paths tens of millions of years apart, and yet, faced with the same underlying mathematical problem, protecting a colony of genetic relatives against overwhelming external threats, evolution arrived at almost the same solution 3 separate times: detonate the individual to save the group. That kind of repeated, independent invention is one of the strongest signals biologists look for when trying to determine whether a trait is truly advantageous, rather than a fluke. When nature solves the same problem the same way more than once, using completely different biological machinery each time, it's rarely a coincidence. It usually means the solution works extraordinarily well, which raises an uncomfortable question. If self-sacrifice for the good of a genetically related group is this powerful an evolutionary strategy, why don't we see anything close to it in more complex animals? Why don't mammals explode? The honest answer is that they largely can't, and largely don't need to, for the same underlying reason. Most mammals, humans included, don't live in colonies made up almost entirely of close genetic relatives working toward one reproducing individual success. Our social structures are far messier, genetically speaking, which makes the sacrifice yourself for the family's genes math far less favorable at the individual level, where you do see faint echoes of the same principle. In extreme parental protectiveness, in soldiers protecting a unit, in emergency responders running toward danger, it tends to be driven by complex layers of culture, bonding, and learned behavior rather than a hardwired biological trigger. The exploding ant doesn't have any of that complexity. It doesn't deliberate. It doesn't weigh options. It simply carries, quite literally, a body built to end itself the instant the colony's survival depends on it. And that's ultimately what makes this story land so differently once you understand the full mechanism behind it. What looks on the surface like a bizarre, almost cartoonish defense tactic, an ant popping like a water balloon, turns out to be one of the most refined expressions of a principle that runs through nearly all of social evolution, that in certain conditions, across separate branches of the tree of life, biology has repeatedly discovered the same unsettling truth. Sometimes the most effective way for a gene to survive isn't to protect the individual carrying it at all. It's to let that individual go.